Hello everyone, it's such a pleasure to share our work here. I'm Mingzhe from the University of Chicago. In this talk, I will introduce how our operating system can utilize a lightweight neural network to provide I/O performance predictability for flash storage. This is a collaboration work with my colleague Levent Toksoz, Nanqinqin, Henry Hoffmann, and Haryadi Gunawi from the University of Chicago, and Edberg Halim from Surya University. Storage is important as we have big data. Our data is doubling every 2 years with approximately 175 zettabytes in 2025. And furthermore, consumers are not only addicted to data, but also more of it in real time. Quantitatively speaking, in 5 years, nearly 30% of our data will be real time. And this further highlights the importance of flash storage devices like SSDs, which can serve large volume data with microsecond level latencies. Major companies are deploying more and more SSD for quick data access, giving SSD market a 15% annual growth rate, forming a 47 to 80 billion market by 2025. However, when people ask whether these SSDs fully solve the real-time challenge, they find that this increasing adoption is not the panacea. Since the start of this adoption, researchers have been calling for new designs and technology to handle the microsecond scale latency interruption from these fast I/O devices, as these killer microseconds can significantly degrade the overall system performance. So why can these devices exhibit unpredictable latency? Experience has shown that the SSD internal complexity is the most significant factor. Due to intrinsic idiosyncrasies, modern SSD need to manage many background operations such as garbage collection, buffer flushing, and wear leveling, which can pose a threat to latency predictability. As a result, devices can show unpredictable latency for individual I/Os even under balanced workloads. And how do current solutions work? One way is to re-architect device internals as done in many white box or gray box works. These approaches are powerful, however, they face a high barrier to widely implement the changes. Compared to them, more adaptable black box techniques attempt to mask the unpredictability without modifying the underlying hardware. For example, some optimized file systems or storage applications to become SSD aware. But they still need to introduce a considerable amount of redesign to the software stack. Given that, among black box approaches, arguably the most popular solution is speculative execution. For example, many key-value stores adopt head requests or hedging, which times its I/O request, sends a backup I/O if there's a stagger, and eventually picks the faster response. Speculative execution is widely adopted as it can mitigate every single slow I/O without requiring much changes in the upper layers. Though speculative execution is simple and capable, it has a major drawback. It is agnostic of the device's latency behaviors. As a result, it must wait, which is very expensive. Well, can we have an approach that shares the black box manner while inferring the device's latency behavior in advance? Yes, this is where learning can help. Here we introduce LinnOS, an operating system that learns per I/O speed in a black box way with a light neural network. With LinnOS, applications can know whether I/O latencies can fulfill the expectations beforehand and further improve their latencies. For example, when a data store sends an I/O to a device, LinnOS can do a quick inference to see if the device can deliver expected latency, and then revoke this I/O if the device can't. Upon that, the data store can easily reuse its built-in replica and failover logic to reroute the I/O to another device, getting a faster response without waiting. To contribute, we developed LinnOS, an operating system that leverages a light neural network to infer SSD performance at per I/O granularity and help parallel storage applications achieve predictable latency. LinnOS supports black box devices and real production traces with up to 97% accuracy, only 6 microsecond low overhead for each I/O, and no extra input required. Compared to hedging and heuristic-based methods, LinnOS can help achieve latency stability at even 99.99 percentile and improve the average latency by up to 80%. Here's the outline for the rest of my talk. First, I will introduce the key design challenges and solutions for LinnOS, followed by the evaluations, and finally conclude. Overall, LinnOS faces 3 major design challenges. First, what should we predict? Should we use binary or multi-class classification or regression to allow LinnOS to produce effective inference with high accuracy? And second, as there are so many available metrics such as I/O offsets, queue lengths, and history latencies, what should we use to predict to allow for a good balance between the accuracy and inference overhead? And third, as achieving 100% accuracy is fundamentally hard, there will be false submits and revokes. How should we minimize the negative impact of these inaccurate cases? The first challenge is the output labeling. Ideally, we want to predict exact latency values or the latency ranges so applications can flexibly tune their actions. However, it is difficult to achieve decent accuracy on black box devices. For example, when we try latency ranges, we found that as I/Os are usually misinferred to the neighbor groups, the accuracy only reaches 60 to 70%. So with these observations, we switch to simpler alternative based on our understanding of performance variability. We've observed that the I/O latencies typically form a Pareto distribution with a high upfront number, as shown in the CDI figure here. As we can see, the latency is likely stable for most of the time and it forms a long tail only at the very high percentile, which naturally forms a slow region that most users worry about. Given that, LinnOS applies a binary classification model that revokes I/O that are inferred to be slow and submit those that are fast. And additionally, to accommodate different distributions, we develop an algorithm called inflection point that automatically finds out the percentile to set up the fast-slow border. Overall, this setting helps LinnOS get a strong focus and achieve high accuracy, as we will show later. The next challenge is to find appropriate input features. From the accuracy aspect, it's preferable to use the finest granularity features such as block addresses of related I/Os, which directly indicate the internal resource contention. This setting does achieve very high accuracy for some scenarios, but also brings significantly high inference overheads, as numerous addresses can occupy up to thousands of features, which require a very heavy model and at least hundreds of microseconds to infer each I/O. This overhead can be even higher than the I/O latency themselves, and is surely unacceptable. So here we take a step back. Instead of using addresses, we switch to the I/O sizes and latencies, which are more aggregate but easier to learn. In this feature setting, when a target I/O comes, we first collect the number of pending page I/Os. As generally speaking, the I/O queue length is a good indicator for latency. However, it does not reflect everything since SSDs can have internal disruptions. Considering that, we also add history I/Os. That is, when an I/O comes, we record the queue length, and when it completes, we record its latency. The way they help is, if there are internal blocking operations, then we will see inverse values, such as short queues but long latencies. So overall, the input features include the current queue length and the queue lengths and latencies of the last 4 completed IOs. The features are split into individual digits. We use 3 digits for the queue lengths and 4 digits for the IO latencies in microseconds. So in total, there are 31 input features. And with this setting, a fully connected neural network with only 3 layers, the input layer, a hidden layer with 256 neurons, and an output layer, can infer with 87 to 97 accuracy, 4 to 6 microseconds overhead for each I/O across various read-write traces and different SSDs. Now let's look at the last challenge: how to mitigate the negative impacts from the inaccurate inference. In LinnOS, inaccurate cases contain 2 categories. The first one is false submits, where LinnOS believes that the I/O will be fast, but actually it's slow. And the second one is false revokes, where LinnOS revokes an I/O that can be actually served fast. The cause of these 2 categories are different. When a false submit happens, the application will see a slow I/O which can take up to milliseconds. On the contrary, when a false revoke happens, the I/O will be rerouted to another device with a failover cost at microsecond level. Therefore, as the impact of false submit is more significant, we apply a bias training that reduces false submits by allowing more false revokes. With a loss function that puts more penalty on the false submits, LinnOS model can further reduce them by up to 68%. Though it's encouraging to see many of the false submits gone, there are still some left, causing long-tail latencies. So to handle them, we mirror LinnOS with hedging and use false submit rates as indicators for hedging percentiles. For example, if during training 7% of the inferences produce false submits, then a P93 hedging will be applied to ascend backup IOs. For cases where false submit rates are low, LinnOS applies conventional P95 hedging to gain further speedup. So to quickly recap, LinnOS predicts per I/O performance as a fast-slow binary classification, and it utilizes aggregate features including current queue lengths, and latencies of history IOs. And to handle inaccurate predictions, LinnOS uses bias training and hedging to mitigate the impact of false submits. With this, LinnOS can achieve 87 to 97% accuracy with 4 to 6 microsecond overhead for each I/O across various SSDs and workloads. But before moving on, here I quickly go through some other designs. LinnOS conducts offline training in the user space and then quantizes the trained model into OS kernel for online inference. LinnOS can utilize coprocessors to further reduce the inference overhead. LinnOS can recalibrate itself by retracing, retraining, and re-uploading weights. If you're interested, please see the paper for more detail. Now let's see how LinnOS can help applications deliver predictable latencies. For performance evaluation, we prepared 2 local flash arrays, one with 3 homogeneous consumer-level SSDs, another one with 3 heterogeneous enterprise-level SSDs. On these devices, there's a storage application that executes SSD-level read-write traces collected from Microsoft production servers. During the trace executions, all read IOs are marked as latency critical, so LinnOS can infer and revoke the slow ones. We assume the data is replicated across devices, so upon revokes, the application can fail over from one device to another. And then eventually, the application will record the latency of read IOs as the major matrix. And for evaluation, we compare 8 methods: baseline, cloning, P95 hedging, a heavier hedging that applies the same threshold as LinnOS, a simple heuristic method that infers and revokes I/O based on the current queue length, a more advanced heuristic that uses the same features as LinnOS without hedging, and LinnOS itself. Here, we will focus on the high percentile latencies. The x-axis here shows the percentile ranging from P80 to P99.99, and the y-axis is the latency. Lines closer to the bottom right indicates better performance. Here, we use Bing workload on the enterprise array as an example. The first line is the baseline, where no action is taken. So as we can see, the tail is quite severe as we see 15 milliseconds at P95 and 34 milliseconds at P99.9. Next is cloning, where each I/O is sent to two devices simultaneously and a faster response is picked. Here's the result. Since the I/O density grows to 2x, cloning does not bring much improvement. Now let's look at P95 hedging, where backup I/O is issued after P95 latency threshold is reached. As we can see, hedging is effective at cutting the tail at higher than P95 percentile. However, it has to wait before sending the extra I/O, resulting in high latency below P95. Given that, we apply a more preemptive hedging which uses the same fast slow threshold as LinnOS, which is usually heavier than P95. This is the result. Here we can see that a heavier hedging, the dark green line, does substantially improve the lower percentile latencies. However, due to more extra I/Os, heavier hedging can see longer tail latency. The next one is a simple heuristic that revokes and reroutes slow I/Os like LinnOS. This method uses the same threshold as LinnOS, but instead of using latency, it uses a current queue length. For example, if LinnOS uses a P80 latency threshold, then this heuristic may use P80 queue length. This is the result. We can see that this heuristic can bring small improvement, but is still far from the best case, as we will show later. We also extend this simple heuristic into a more advanced version. In short, in addition to following this simple heuristic, it also checks the recent history I/Os to see whether they met high latency with low queue length, indicating an internal disruption. If so, the I/Os will be revoked unless the current queue length drops to a low value. Here shows the result. In general, this more advanced heuristic can outperform the simple one, but still away from the best case. Additionally, this mechanism faces a difficulty of manually tuning the large space of parameters. Now let's look at LinnOS, first without hedging. As a learning-based method, LinnOS can auto-tune and use its numerous ways for revoke decisions. And here's the result. Without hedging, LinnOS can further improve under P95. However, we also see some false submits which causes long-tail latencies. With that, LinnOS uses hedging to cover the inaccurate cases, where hedging percentile is 100% minus the false submit rate. As we can see, LinnOS, the blue solid line, can achieve stable latency at even 99.99 percentile and outperform all other methods, showing how learning can help improve real-time performance. Here, I will quickly go through some other evaluations. LinnOS brings stable latency for various production workload and devices. LinnOS helps cut the average latency by 9.6 to 79.6% compared with other methods. LinnOS achieves high accuracy with low false submit rates with bias training. LinnOS can support other public traces, and the file systems and data stores like MongoDB can easily adopt LinnOS with minor changes. To conclude, by using a lightweight neural network, LinnOS can predict per I/O latency behaviors of SSDs in a black box way, with great accuracy and low overhead, bringing more predictable performance to flash storage. This is the end of my talk. Thank you for listening.